Okay. Great. So I'm Anirudh, and I'm a grad student at MIT, and I'm going to be talking about a system for programmable packet scheduling at line rate. This is joint work with folks at MIT, Barefoot Networks, Cisco, and Stanford. So the title of this talk is Programmable Scheduling at Line Rate. Let me break each of those two parts down. So when I say programmable, we're really asking this question: can we express a new scheduling algorithm, possibly something you haven't even thought of today, and have it run on a switch? And when I say line rate, I mean a switch that runs at the highest capacity supported by a communication standard today. This is currently 10 gigabits per second on Ethernet. Increasingly, this is becoming 40 and 100 gigabits per second. So the term line rate should immediately make it clear why we're not referring to doing things on a software router, on an NPU, on an FPGA. While these platforms are extremely programmable, and in principle you can express like any arbitrary scheduling algorithm on these platforms, they usually, historically, they've come with between a 10 and 100x performance loss relative to line rate switches. So with this emphasis on line rate programmability, let's look at what the state of the art in line rate programmability is. Because after all, one of the goals of software-defined networking was to make commodity switches at line rate programmable. So why doesn't that suffice? So if you look at a switch, part of this echoes what Nate said. If you look at the internals of a switch, there's a parser that turns bytes into packets. There's a bunch of lookup tables in the ingress pipeline which process those packets. There are output queues in the scheduler, typically a few for each output port. There's a similar egress pipeline, and then a deparser serializes packets back on the wire. Now, over time, different parts of this picture have become more programmable. OpenFlow was obviously the first instance of this, which allowed a unified interface to match action tables across several switches. And with OpenFlow, you could match on a fixed set of fields like TCP port, IP address, and carry out a fixed set of actions: drop a packet, decrement the TTL, and so on. There's been a more recent line of work characterized by RMT, PIFO, FlexPipe, and so on, where there's a trend towards more protocol-independent pipelines, where there's a programmable parser, and as a user, you can program a new protocol format. And once you have a new protocol format, you can use fields in that format in your match action table. So you get flexibility on the match side by using new fields. And you also get flexibility on the action side by composing actions arbitrarily from a small set of instruction set operations, if you will, where you can do simple arithmetic on fields. Now, amidst all this, about 7-8 years of work on programmable switches, one part has by and large remained the same, which is the scheduler. Switches today still provide just a few scheduling algorithms, typically things like deficit round robin and strict priority scheduling. So as a user, you can go and tweak knobs in these algorithms. You can change the coefficients, but fundamentally, you can't change the algorithm itself. So which raises the question, why has programmable scheduling been so elusive so far? And it's not for a lack of algorithms. There's been plenty of algorithms, as Nate showed on his slides. But despite all this, despite more than 2 decades of work on scheduling algorithms, there's no consensus on the right abstractions for scheduling. So this is in contrast to the rest of the pipeline, where you can use a parse graph to succinctly capture different protocol formats for parsing, and you can use match action tables to express several forwarding policies. There is no such abstraction for scheduling. And we could throw up our hands and say, let's just put a CPU in the fast path so that you can program whatever scheduling algorithm you want. But when a scheduler needs to make a decision every nanosecond, as is typical in a switch pipeline, that approach doesn't work either. So the primary contribution of this talk is an abstraction for programmable packet scheduling. And it's based on this observation that many algorithms determine transmission order as packets arrive. Put differently, the relative order of packet transmissions of packets that are already in the queue don't change with future packet arrivals. So 2 examples that show this, shortest job first and first come, first serve. In both cases, the order is determined by some attribute that is known in packet arrival, either flow size or the arrival time itself. So this is called a push-in first-out queue, where packets are pushed into an arbitrary location based on a priority, but they're always dequeued from the head. Now, this was proposed in a paper in the late 90s, but at that point it was used largely as a proof construct. What we show here is that it can be used practically as an abstraction and is also feasible at line rate. So how do you use a PIFO to build a programmable scheduler? At its core, a PIFO is just this mechanism that allows you to drop a packet into a particular location using a programmable priority field. Now, if you think of a scheduler built using a PIFO, it really has two parts. The first part is computing the priority for the packet, which is programmable. And the second is the fixed part, which is simply enqueuing and dequeuing into a push-in first-out queue. And these two parts really have very different performance requirements. The fixed part, which is the enqueue and dequeue operations on the queue, needs to run at line rate. The programmable parts process each packet independent of other packets, and they don't even need to run at line rate. And they can run at various different points in the network. And what do I mean by that? They can run on the ingress pipeline of the same switch where you're running the scheduling algorithm. So this could exploit pipelines and programmable switches like the RMT architecture. They could run on an upstream switch, which provides similar capabilities. Or they could run all the way up at the end host. And I'll show a few examples of how moving this computation around through the network allows us to do different kinds of scheduling algorithms using a PIFO. So the first example is pfabric, which is a recent data center scheduling algorithm, which at its core just does shortest remaining processing time. And here, the end host tracks TCP acknowledgements to determine the remaining number of bytes in each flow. And for a given packet, it looks up its flow and sets the packet's priority to the remaining size in that flow. And the scheduler's job is to just respect these priorities. Another example is weighted fair queuing, and this will show you how you can leverage computation on the switch. So most algorithms for weighted fair queuing use some notion of virtual time. And so the way this works in a simplified representation is you take the packet, compute its flow, and for a given packet, write down its virtual start time as the finish time of the last packet in that flow. And at the same time, you update the finish time. So this is persistent state that's maintained on the switch. So you update it for the subsequent packet, and you set the priority again to the virtual start time. And the job of the PIFO is simply to enforce these priorities. As another example of a non-work conserving scheduling algorithm, we look at traffic shaping, whose job is to simply restrict a flow to an absolute bandwidth cap. And with traffic shaping, there's some stateful algorithm that updates tokens based on the burst size and like the token update rate. And then the transmission time of the current packet is the present time plus whatever time it takes to make up the deficit in tokens. And again, this transmission time, p.send, becomes the priority itself. And like the job of the PIFO is simply to release the packet when that particular transmission time arrives. So far we've looked at several examples where a PIFO can be used for scheduling algorithms. But common to all of these algorithms is the property that the relative order of packet departures doesn't change once packets are in the queue. Now, this is reasonable for several algorithms, but there are practical algorithms for which this is not the case. And the most notable of these algorithms is any form of hierarchical scheduling. And it's been shown that you can't do hierarchical scheduling with something resembling a priority queue, which is what a PIFO is in essence. So at the same time, we show that we can take a combination of such PIFOs and use it to implement hierarchical scheduling. And as an example, for concreteness, let's look at hierarchical packet fair queuing, which basically does fair queuing across a set of classes, and then recursively does fair queuing within flows belonging to that class. And with a minor change to the PIFO semantics, which allows us to enqueue not just a packet, but also a pointer to another PIFO, we're able to realize HPFQ using a combination of PIFOs. So more concretely, we have this PIFO tree, which is sort of isomorphic to the hierarchy itself. And the root level of this tree is a root PIFO that does weighted fair queuing across classes A and B. So its pointers point to PIFO A and PIFO B, and the job of PIFO root is to do weighted fair queuing across the classes. At the next level, PIFO A and PIFO B each do weighted fair queuing across their constituent flows. Now, the flow, when a packet comes in, actually, when a packet is dequeued, is you first pop the head packet from PIFO root. It gives you a pointer to either PIFO A or PIFO B, and then you recursively go to one of those two, and then dequeue a packet from either of those two PIFOs. So to summarize, here's a one-slide overview of the PIFO abstraction. It's a sorted array that lets us insert an entry, which can either be a packet or PIFO pointer, into a PIFO based on a programmable priority. Entries are always dequeued from the head. If an entry is a packet, your job's done. You basically just transmit the packet. If the entry is a PIFO, you dequeue it and continue recursively. Now, the reason I lay out these rules here is to show that there's a specific set of semantics by which we can compose PIFOs, and there's a specific space of programs that we can write to compute the priorities for the PIFOs. And together, they enable a rich class of scheduling algorithms to be expressed using the PIFO abstraction, which is more than the specific examples that I just outlined. So this is all well and good, but is this feasible in hardware? And so we decided to see if we could implement a PIFO with about 128K entries. Now, why 128K? It turns out that's more than sufficient for most switching chips today. And the naive way to do this is to just build an array with 128K entries, and as a packet comes in, you compare it in parallel to all of those 128K entries and figure out exactly where to drop it in the array. Now, as you probably realize, this doesn't quite work because at the physical level, this requires 100K comparators, which is kind of a non-starter as far as hardware design goes. So the key technique we use is to break up this problem into parts that can be managed in parallel. So what we do is something analogous to bucket sort, where we break up the 128K elements into 128 element mini PIFOs and 1,000 such mini PIFOs. And so each of those 128 elements is now small enough that you can actually brute force the insert operation into them. You can compare against all those elements in parallel and just drop the packet there. But the problem has now moved to this range search CAM, which needs to tell you which of those mini PIFOs you actually need to do the insert into. And that's the most uncertain part of this design. So we synthesized this on a 16 nanometer industry standard technology node. And we were actually a little surprised to see that it met timing at 1 gigahertz, which is the typical clock rate of switch pipelines. And the reason that this works out is because it turns out transistor sizes have scaled to a point that you can actually compare a single priority against all those ranges in parallel and still meet timing on a small enough technology node like 16 nanometer. Now, what's the cost of this? We have about 5% area overhead in die size relative to a baseline chip such as the Broadcom Trident. But in return, you're able to program arbitrary 3-level hierarchical scheduling algorithms with an unbounded number of flows. By contrast, the Broadcom Trident, which is kind of representative of many switching chips today, provide you fixed 2-level hierarchical scheduling over about 10 queues. More philosophically, we think this design challenges the conventional wisdom that sorting is hard at line rate. If you look at quite some literature that looks for O of 1 approximations to fair queuing, they all start off with this assumption that the virtual time calculation in weighted fair queuing is just hard. And what we see here is that technology has scaled to a point where it might be worthwhile revisiting that assumption. So to conclude, I hope to have convinced you that line rate programmable scheduling is within reach, and we view PIFOs as bringing to scheduling what match action tables have done for forwarding. And this has two concrete benefits. As a network operator, you now get to program new scheduling algorithms without having to repeatedly haggle with your vendor about what makes the cut in silicon and what doesn't. And as a chip designer, you get to design and verify one piece of hardware, which is a PIFO. The 10 scheduling algorithms that are built on top of the PIFO just become merely software configuration, and those are much easier bugs to fix than hardware bugs. So with that, I'll conclude. Thank you.